Welcome to The Grid, your monthly connection for critical engineering insights from Quantic Electronics. Today, we're featuring Quantic Wenzel of Austin, Texas, a leader in high performance frequency sources for mission critical applications. In this webinar, key questions for selecting fixed frequency sources in RF and microwave, sales engineer Michael Glass and senior RF design engineer Richard Kohler will explore the vital role of these sources in systems like radar, electronic warfare, and communications. They'll discuss how factors such as phase noise, frequency stability, spectral purity, and jitter significantly impact overall system performance.
My name is Richard Kohler, and I want to thank you for joining us today to review some key parameters for selecting RF and microwave fixed frequency sources. I've been a member of the technical staff at Quantic Wenzel for many years. I've held several positions with the company in manufacturing and product design, including several years as a member of Charles Wenzel's research team.
And I'm Michael Glass, one of the RF sales engineers here at Wenzel Associates, Quantic Wenzel. I've been with the company for 15 years. That's 10 years in production and 5 years on the sales team.
Today's agenda will be an introduction to our frequency control and timing solutions. What are the main types of fixed frequency sources and which one is right for my application? What performance specs truly matter for my system? What custom features should I consider to meet my system requirements? How do I ensure my fixed frequency source will be reliable? What lead time should I plan for? And how can I stay on schedule? Then we will sum it up and there will be an opportunity for some live questions and answers. So today, Michael and I are going to give you an introduction to our frequency control and timing solutions. But first, I'd like to tell you a little bit about our company. The company was founded in 1978 as Wenzel Associates by two engineers, Liz Ronchetti and Charles Wenzel, who is our namesake, and Dina Cole, who managed the day-to-day business and MRP activities of the company. From that three-person start with a couple of oscillator designs, the company's grown into a timing and frequency solutions provider with an extensive portfolio of RF systems, sources, and modules. Quantic Wenzel is today a business unit of Quantic Electronics. We've just recently celebrated the ribbon cutting on a new 45,000 square foot manufacturing facility here in Austin, Texas.
Here at Quantic Wenzel, our core competencies are our low noise OCXOs, ovenized crystal oscillators. We provide those low noise, low phase noise, and high frequency stability oscillators in multiple markets with advanced vibration compensation, low G sensitivity performance, temperature deviation resiliency, and long-term aging. Our oscillators are used in multiple applications, including ground-based and air and ship-based systems, for radar, quantum computers, communications, and EW systems. As I mentioned, our key technologies are ovenized crystal oscillators, or OCXOs. We also manufacture PLOs, multiplied crystal oscillators, or MXOs, provide vibration compensation systems, IMAs, or integrated microwave assemblies, low noise distribution amplifiers, and many more. Our type of systems that we design include integrated microwave assemblies, which provide outputs from anywhere from 5 megahertz to 30 gigahertz and beyond. These employ OCXOs as well as rubidiums for long-term stability, and they also offer phase lock options. Our instruments provide multiple frequency sources, again in the same frequency range from 5 megahertz up to 30 gigahertz, multiple outputs from upwards of 24 plus outputs, and these are available in anything between a 1U and 8U rack solutions. We also offer space qualified solutions for LEO, GEO, and deep space programs. These are for OCXO and synthesizer solutions. We have a broad range of OCXOs that provide outputs from 5 megahertz and our small form factors up to 320 megahertz. We also incorporate rubidiums into our OCXOs for short-term and long-term stability and for excellent 1 PPS locking as well. And then finally, we also provide VPX form factors for custom form factor applications where ruggedized environments are expected. So next, we're going to talk about the main types of fixed frequency sources and which one is right for my application. We know there are many options to choose from, and there is no one-size-fits-all fixed frequency source for your application. A few options include direct digital synthesizers, or DDSs, oven-controlled crystal oscillators, or the OCXOs that we manufacture, these multiplied crystal oscillators, which are up-converted versions of the OCXOs. Also available are synthesizers that integrate voltage control oscillators, or VCOs. Also available are the temperature-controlled crystal oscillators, TCXOs, VCOs standalone, dielectric resonator oscillators, or DROs, as well as VCSOs, voltage control SAW oscillators. Each type of oscillator has its own strengths and weaknesses. DDSs, for example, provide excellent agile signal generation for multiple frequency resolution and generation. OCXOs also provide ultra-stable timing, which are best for phase noise and stability in controlled environments. TCXOs are small and low power, which are excellent for portable systems. They're also lower cost and with excellent temperature compensation. VCOs are tunable local oscillators, which provide fast tuning and are often integrated into PLLs. DROs provide high frequency for low phase noise at higher frequencies and higher offsets. PLOs are clean frequency PLLs, which are often locked to a lower noise frequency reference. Our own MXOs are excellent for high frequency outputs with a low base frequency. And then VCOs, when integrated with the synthesizer, provide for frequency agility while phase locking as well. VCSOs are available for high environments with good vibration resistance and temperature stability. There are always trade-offs and system-level considerations when considering the options for a frequency synthesizer or generator. When the requirement needs low or ultra-low phase noise, you may prioritize an OCXO or a PLO or an integration with a PLO or a DRO for higher frequency outputs. When tight space or power constraints are most critical, you may consider a TCXO or a VCSO, or perhaps a VCO integrated with a base solution. When the frequency agility or tuning is required, DDSs or synthesizers with VCOs options are often chosen. When a high frequency output is needed, an MXO or DRO make an excellent solution, and using the multiplication up conversion to provide the higher frequency solutions. And then finally, when you integrate into a modular systems, for instance, a VPX, when you're looking to integrate a low frequency oscillator or frequency solution into something like an open VPX form factor, it's often important to choose something that has low swap-C performance.
Thank you, Michael. Now let's take a look at what performance specs truly matter for my system. When we talk about performance specifications in timing and frequency generation, we're talking about the stability and purity of the frequency signal being generated by an oscillator. The stability of a frequency source, and I'm now speaking about crystal oscillators in particular, is affected by changes in the environment, temperature, vibration, altitude, but also by the circuit design and selection of the components inside the oscillator. Some of the key performance specifications to consider, and we'll see these in a moment on our specification sheet, are the G sensitivity, vibration sensitivity to vibration, the aging rate, power consumption, spurious content, and temperature stability. What we see here is a typical specification sheet, this one in particular for a 10 megahertz Onyx oven-controlled crystal oscillator. Looking at the specifications sheet, you can see that we have specified things such as the aging rate of the oscillator. This would be the frequency aging. The phase noise performance. This is the amount of random noise or signal purity. The temperature performance. This is how much the frequency will change as the environmental temperature or conditions change. And also some information about power consumption, harmonic performance, spurious performance, and performance under vibration. Let's talk a bit about noise. Jitter and phase noise are both ways of describing the short-term rapid fluctuations or stability of an RF signal, but they're usually characterized in different domains: time for jitter and frequency for phase noise. In essence, phase noise in the frequency domain corresponds to jitter in the time domain. So a high jitter measurement impacts the phase noise measurement, and a high phase noise measurement is an indicator of increased jitter. While the total jitter measurement combines random and deterministic effects on signal stability, phase noise is defined as being random fluctuations in the phase of the signal. And phase noise is what I'd like to look at a bit closer today. Phase noise in RF signals refers to the random short-term rapid fluctuations in the phase of a signal, typically caused by imperfections in oscillators and signal generators. These fluctuations spread the signal's power into adjacent frequencies, creating sidebands around the main carrier frequency. Phase noise is present on all RF signals and affects the precision of systems. Some examples of how phase noise affects systems are bit error rates in data transmission, clarity of medical images, and the ability of radars to identify and discriminate between targets. For example, in a Doppler radar used to detect the velocity of moving objects, let's say vehicles and aircraft, if the radar signal phase noise is high, the noise sidebands around the carrier frequency can mask or bury the Doppler shift of the signal, making it hard to distinguish the target from the noise, leading to missed or false detections. In an age where swarms of objects moving at very slow or hyper-fast speeds need to be detected, and all of this detection information needs to be communicated in real time to multiple platforms over land, air, and space-based communication systems, you can begin to see the importance of having signal sources with low and ultra-low phase noise. Phase noise is usually depicted on a logarithmic plot, which shows the noise sideband or skirt present on the carrier signal. The measurement shows the power of the noise in relation to the power level of the carrier frequency. So for a given offset in hertz from the frequency of the carrier signal, we can determine the delta, or how far down in decibels is the power level of the noise compared to the power level of the carrier. So a measurement of minus 170 dBc per hertz would tell us that the noise power present at that frequency offset is 170 decibels below the power level of the carrier signal and is measured in a 1 hertz bandwidth. The phase noise is highest close into the carrier and drops to a floor as you move further away in frequency from the carrier frequency. Phase noise is actually present on both sides of the carrier, but we typically assume the phase noise is equal on both sides of the carrier and just discuss the measurement of one side, thus the SSB, or single sideband phase noise designation. Typically, a phase noise specification is a table of frequency offsets and corresponding minus dBc per hertz values. Again, this is the level in dB down from the carrier power. The listed frequency offsets are usually in decades: 1 hertz, 10 hertz, 100 hertz, 1 kilohertz, and so on. The phase noise plot also shows the noise present between these offsets, and the slopes between the points generally follow the shape seen on this plot if the oscillator is performing properly. If these shapes do not follow this typical plot, then this will tell the technical staff where to begin looking to find the cause of the noise.
All right, so next we're going to talk about potential custom features that you may consider when you may need them to meet your system requirements. Quantic Wenzel provides vibration isolation and compensation on many of our products, which are available to the public. These provide passive vibration isolation with the use of shock mounts, but we've also introduced active vibration compensation, which allows for an active feedback system which can provide additional correction of the phase noise in a vibration environment. Here we can see the combination of an active vibration system with a passive vibration system, compensation system, in order to provide improvements by as much as 15 to 20 dB of phase improvement based on the G sensitivity of the crystal and the compensation system. Wenzel also offers external reference locking, which allows for precision locking of an external frequency reference and providing multiple frequencies outputted from our low noise OCXOs. These are crucial for phase coherence across multi-node RF systems, which are often used in multiple array systems. Quantic Wenzel can also provide specialized form factors. This may include rugged assemblies for harsh environments, for example, a VPX form factor. Other considerations included SWaP-C, which is size, weight, and power and cost, which may be considerations for demanding physical power and cost limitations in your system. You may also consider custom interfaces, including multi-pin connectors for interface for your RF signals, as well as cooling and heat dissipation methods, and EMI and EMC vulnerability, and then finally, hermetic enclosure options.
So, how do I ensure my fixed frequency source will be reliable? Well, my first recommendation is to purchase your frequency source from a manufacturer with a long history of designing and manufacturing reliable oscillators and systems. Quantic Wenzel comes to mind. Quantic Wenzel has a heritage of manufacturing for the most demanding environments: defense applications, all services, space, low Earth orbit and deep space, radar, fixed and mobile, and a host of communications and data transmission applications. Each of these industries relies on mill and industry standards for the supply chain manufacturing and testing. Our procurement, handling, manufacturing, and testing processes meet or exceed applicable industry standards. If it's in your specification or source control drawing, Quantic Wenzel can work to it.
You may also consider what lead times should you be planning for, and how can you stay on schedule when you're placing your order with us. You must understand that lead times can vary and that there are various levels of complexity and customization for each of these products. When applicable, it's important to try to pick a catalog part, which we have many of, so that you can not only use the breadth and heritage of our product history, but also parts that have already been designed and are ready to ship in a shorter period of time. We want to make sure that we shorten the supply chain variability, so we try to use as many parts over as possible, as well as the timing that it takes for testing and qualification and alignment. Quantic Wenzel knows that staying on time is important for your schedule and your program. With proactive planning and workflow adjustments, Quantic Wenzel will work with you with early engagement and allowing for buffer time so that we can continue to deliver your products on time with the quality that you expect. With ongoing communication, Wenzel will continue to open the dialogue and make sure that the products that we deliver are meeting your demands. Of course, we have to consider export compliance requirements, and that will also be considered for our delivery schedule.
So Michael has taken us through some of the various products that we make here at Quantic Wenzel. And I just wanted to kind of close by saying that the phase noise of a system depends on how low noise is the local oscillator from which the system frequencies are derived. But we also need to consider the noise added by circuits used to multiply and divide the frequency, or by signal conditioning circuits, filters, amplifiers, phase lock loops, distribution amplifiers, and so on. So it's critical that the local oscillator is chosen to be sufficiently low noise so that with all of the circuits connected in the system, the end result is a signal low enough in noise to meet the system requirements. At Quantic Wenzel, we offer a range of modules and systems with each circuit designed and optimized to take advantage of the very low phase noise levels available in our oscillator products. Our sales engineers are experienced in working through these topics and can help you choose the performance level that is appropriate for your application. Thank you for joining us today, and I hope the information we presented gives you a better understanding of the products we manufacture at Quantic Wenzel. And now we'd be happy to answer a few questions.
Can your OCXOs be used with new technologies like RF SoC?
Absolutely. And in fact, Michael and I were discussing a bit of that this morning. So you always want to have a low possible signal source from which you are going to derive any other source. So for all of these types of systems, yes, at the heart of it somewhere there will be a low noise signal source, and if you want a real low noise signal source, you're going to have a crystal oscillator, either a TCXO or an OCXO.
With external frequency locking, what would happen if we lose the external frequency locking connection?
Well, what will happen then is the oscillator will then go into what we call a free running state. So all oscillators will drift to some extent over time, and there are some holdover circuits that can put little corrections in there if you can predict what the free running state will do. But so generally, the oscillator will continue to function, but the oscillator frequency may begin to drift over time. So depending on how long you're unlocked, that drift error will get greater. But then when that external reference is reconnected, the phase lock loop will then do what it does, and it will lock back onto that external signal and pull and tune the oscillator back on frequency, the follower oscillator. Important to remember is that the phase lock loops have loop bandwidths, and inside that loop, our output signal is going to have the characteristics of that external reference, and outside of that phase lock loop, it will have the characteristics of our oscillator. So oftentimes a Wenzel oscillator can be used to clean up a reference signal. So you'll have the precision, let's say, of an atomic clock, but the phase noise performance of a crystal oscillator. And that's actually a common application. And we have a full line of phase locked oscillators and products.
Can you share any insights into Quantic Wenzel's approach to research and development?
It's continuous. It's an ongoing effort. So I'm only kind of half joking when I say just as soon as our engineers design something and our applications engineers turning it into a product, the next phone call we're going to get is somebody asking us, can we have a 2 or 3 dB improvement in phase noise? Can we have a little bit more power? So we are continuously doing that. And like I was just mentioning, we are continuously having to be vigilant to keep the phase noise performance of our products at these ultra low levels. So sometimes it's batch to batch of it can be different date codes on reels of semiconductors that come in and give us slightly different performance, and then we have to react to it. So we're always doing that research. I will always also say that when we get inquiries for systems and things, a lot of times it is someone, a big defense contractor, something trying to do the next generation of radar or electronic countermeasures or something. So they're always trying to push the envelope in performance, and that, of course, flows down into our products. So we're always, either we're working to a spec that we're trying to meet, trying to keep our current products at the ultra low levels, or we just become aware of new components that are available in the marketplace, and then our engineers will take an interest and start seeing what they can do with them.